Venezuela is a South American nation sitting atop one of the largest concentrations of oil on Earth, with more than 300 billion barrels hidden beneath its soil. This vast underground wealth has long attracted global attention, including from the United States, where advanced refineries are capable of processing Venezuela's unique crude. Yet oil underground is only potential power. It becomes real economic force only when it can be extracted, transported, refined, and sold. For Venezuela, this challenge has shaped the country's modern history. Alongside drilling operations, the nation has built enormous cross-country steel pipelines that function like a man-made river, carrying crude oil across thousands of kilometers. From the heart of the Orinoco Belt to coastal export terminals, these pipelines quietly move energy day and night, forming an invisible infrastructure that links remote inland oil fields to global markets. Venezuela holds the largest proven crude oil reserves in the world, representing nearly 17% of global reserves, most of them concentrated in the Orinoco Belt. However, the majority of this oil is extra heavy crude, thick, viscous, and high in sulfur. Unlike light crude, it cannot be easily refined and requires highly advanced processing systems, many of which are located in the United States. This reality makes extraction and transportation far more complex and expensive. Over the decades, these technical difficulties, combined with political and economic instability, have contributed to the decline of Venezuela's oil industry. To overcome the geographical challenge of moving heavy crude from deep inland regions to the coast, Venezuela developed massive pipeline networks. These steel arteries transport oil from production fields to northern ports, where it is loaded onto tankers and shipped to specialized refineries abroad. This constant, silent flow has often been described as a steel river of oil, sustaining the country's economy even as visible production struggles continue. The construction of a major oil pipeline begins long before any trench is dug. It starts with the manufacturing of the pipeline segments themselves. These pipes are made from high-strength carbon steel, similar to those used in major crude oil transport systems around the world, designed to withstand high internal pressures, mechanical stress during installation, and extreme temperature changes. Rectangular steel plates are cut to precise dimensions, calculated to form cylindrical pipes with diameters approaching 1.8 meters and wall thicknesses of around 25 millimeters. The plates are fed into multi-axis rolling machines that gradually bend the steel until the edges meet, forming a pipe shell. Longitudinal welding seals the seam, after which the pipe passes through controlled water cooling to stabilize the weld. Each pipe is polished to remove sharp edges, inspected for accuracy, and prepared with chamfered ends to ensure strong, leak-free welds in the field. Typically, each segment measures around 12 meters in length, balancing transport practicality with the need to minimize the total number of joints. Once fabrication is complete, the pipes are stored in open yards, organized, labeled, and tracked for logistics control. Specialized transport vehicles then haul the pipe sections hundreds of kilometers to the construction site. Along the pipeline route, large staging areas are established where engineering teams perform final inspections, checking straightness, coating integrity, and identification markings. Before excavation begins, the route is cleared and graded, and temporary service roads are built to support heavy machinery and transport vehicles. In Venezuela's harsh environments, dust suppression and ground stabilization are essential to maintain visibility and protect workers. Excavators then cut trenches along the surveyed alignment to precise specifications. In mountainous or rocky regions, controlled blasting is used to carve trenches directly into solid rock. After excavation, a carefully prepared bedding layer of fine soil or sand is laid at the bottom of the trench to distribute loads evenly and prevent stress concentrations on the pipe. Pipe installation proceeds in a carefully choreographed sequence. At welding stations, hydraulic internal lineup clamps align pipe sections with extreme precision, holding them concentric during welding. Automated welding systems, supported by large crews and specialized equipment, can complete hundreds of welds per day on large diameter pipelines. Each weld undergoes ultrasonic testing to detect internal flaws, before field joint coatings are applied to protect against corrosion. Side boom tractors then lift long strings of connected pipe, keeping them suspended and aligned as they are lowered gently into the trench. Surveyors continuously monitor elevation and curvature to prevent residual stress. In steep or unstable terrain, shorter pipe strings, slower installation speeds, and additional anchoring measures are used to maintain control. Once the pipe is in place, the trench is backfilled in layers, starting with fine material to protect the coating, followed by compacted soil to ensure long-term stability. After installation, the pipeline begins its true purpose, transporting crude oil from inland production fields to coastal export terminals. From these ports, tankers carry the oil across oceans on journeys that can take weeks or months. When the crude reaches advanced refineries, particularly in the United States, it enters a complex transformation process. The first major step is fractional distillation, where crude oil is heated to around 650 to 670 degrees Fahrenheit and fed into towering distillation columns. Inside, hydrocarbons separate according to boiling points, with heavy residues settling at the bottom and lighter products rising higher. Gasoline condenses in the midsection of the column, while gases like propane and butane collect at the top. However, this initial gasoline is not yet suitable for engines. It must undergo further processing such as catalytic cracking, reforming, and blending with additives to meet modern performance and environmental standards. Only then is it stored and distributed to fuel stations, completing the journey from thick underground crude to refined fuel. The story begins even earlier at the extraction stage. In Venezuela, oil is primarily extracted on land through an expensive and technically demanding process. Geological surveys using seismic imaging and exploratory drilling identify promising reservoirs. Wells are drilled vertically, and then steered horizontally for thousands of meters to maximize contact with the oil-bearing rock. Hydraulic fracturing is often used to release hydrocarbons trapped in tight formations, pumping water, sand, and chemicals underground at immense pressures. What reaches the surface is a mixture of oil, gas, water, and sediments, which must be separated and treated before transport. While this technology has helped unlock massive production elsewhere, it is costly and carries environmental risks, if not carefully managed. Together, these stages form a vast, interconnected system. From deep underground reservoirs to steel pipelines stretching across deserts and mountains, from coastal ports to distant refineries, Venezuela's oil travels through a global network of engineering, logistics, and economics. This steel river of oil has connected remote regions to industrial centers and powered economies far beyond Venezuela's borders. As global politics shift and energy strategies evolve, the future of this flow remains uncertain, but the scale and complexity of the system behind it reveal just how much effort is required to turn buried oil into usable energy.